Hello and welcome friends. In the last lecture, we discussed about composition of the atmosphere, characteristics of the atmosphere, in addition to the dynamics associated with the atmosphere in terms of primary parameters and secondary meteorological parameters. As a few of the primary parameters, we gave consideration to wind, atmospheric stability, temperature, in addition to the mixing height. So in this particular lecture, we wish to understand some more things of the first meteorological parameter, which is wind. So here we wish to discuss about the importance of the wind systems in the context of the air pollution studies, certain basic instruments that can be used in order to measure the wind speed as well as the direction. We'll discuss about the construction of the wind rose diagram as well as concept of geostrophic and gradient wind. So as you learn the content, you will be able to explain the importance of the wind systems in air pollution studies. Also to use the various tools for the expression of the wind velocity as well as the direction, and also to explain the concept of the geostrophic as well as the gradient wind with the associated terms. Let's have a brief review as far as the wind systems are concerned in context of air pollution. As the pollutant is emitted from a certain source, it moves according to prevailing wind patterns. Hence, the fate of that particular pollutant is decided by locally existing wind system. Hence, it is essential to understand the local wind systems in order to know the transport and the dispersion of the air pollutants. Air moves in the horizontal plane as well as in the vertical plane. These vertical motions affect both weather as well as mixing of the pollutants and sometimes settling as well as resuspension of the pollutant. The upward vertical motion could be caused by lifting the air current over the terrain, weather fronts, and convergence towards low pressure centers. As we move ahead, we'll be able to understand the lifting over the terrain and some concepts associated with local wind systems for the transport as well as the dispersion of the pollutants. Here let's understand about the weather front. So if we consider two air masses, each could be having its own density, each could be having its own velocity, temperature, as well as the humidity. Hence, we have to treat that two individual air masses differently. As we are discussing, this air is not static phenomena, but it is associated with the motion, it is associated with the energy, and it is governed by so many factors. Hence, there is not any concrete compartment as far as separation of these two masses are concerned. There will be some transition zone from one mass to other mass. So, this weather front is the boundary in transition separating that air masses with different characteristics. As we discussed about the type of the fronts, we can categorize it as cold front, warm front, stationary front, as well as occluded front. As we refer to the weather map, it will be using some specialized symbols. So here what you see is blue line with certain arrow-like triangles that are resting on that particular line. So it indicates the direction of the cold mass moving towards the warm mass as far as this first category, that is cold front, is concerned. So in case of the cold front, cold mass moves under the warm mass. So this warm mass is less dense, and hence, being this cold mass very dense, this warm mass can be easily pushed up, and as it goes up, it will be getting cooled, and it will cause the raining as well as the thunderstorms. As the front passes, the cooler temperature and the dry air alter. As we consider the second case, here it indicates a red line and certain semicircular spots showing the direction of that particular front. Being red, it represents the warm front. So in the warm front, hot air pushes against the cold air. It is obvious that this hot air will be less denser, and it will be difficult for the hot air, that hot air mass, to push the cold mass. Hence, this hot mass, that hot air mass, rises above the cold mass, and accordingly it will attract light rain as compared to this cold front that could have raised the intensity of the rain, as well as there will be humid temperature. The third category that we see, that is the combination of air mass which is hot and which is cold. However, this particular boundary is not moving because neither of these particular air masses have the enough energy in order to alter that particular front. So to say, both the hot masses and cold masses are balancing each other. This situation will lead to cloudy and overcast with light showers. These conditions usually do not change until another system passes over. The fourth category is occluded front. You can refer to this lower sketch. Here, a warm front is moving and it is immediately followed by certain cold front. Warm front being less dense, it will be traveling in the direction with, say, small velocity as compared to the cold mass which is moving behind. So this cold mass can easily push this warm mass. It crosses over and it forms the combination which is called as occluded front. In addition to these particular fronts, we will be referring to some terms such as convergence and divergence. In context of meteorology, this convergence refer to the horizontal radial inflow and it is getting accumulated, as well as that particular rate of accumulation is also considered under this convergence. So as it comes together, it does not have any place to go. Hence, the air mass rises vertically above, and as it creates the void, the process will be continuing to attract the flow in the inward manner. Contrast to this low heating system, there is divergence. So as we consider here, in case of divergence, the air mass is sinking below as there is a radial outward movement of that particular air mass, and this is making up near high pressure systems. We should also consider the concept of the direction and the speed in view of the movement of the pollutant. So, as we consider this x direction and y direction, as the pollutant is getting emitted from a certain source, it would be drifted in the direction of the x. It will be dispersed in the direction of the x in the horizontal plane. Whereas, as we consider the horizontal lateral direction, which is normal to this x direction, it will be y, and hence it is said to have the diffusion in y direction as well as vertically above and below in z direction, depending on the placement of the source. Gustiness is quick and sudden increase in the speed of the wind, which is caused by the friction. So if we consider some topographical features, maybe hillock or certain artificial structures, say buildings, so it will cause the hindrance in the direction of that wind, as well as various topographical features depending on their geographical placement will be getting heated in different manner, and hence it will also cause the gustiness. So this gustiness is in proportion with the speed. As we consider the wind and its movement, Say here, as you see, certain windward direction is given as well as the leeward direction is given. So if there is certain presence of dense barrier, it will be effective at slowing the wind near that shear belt, but not far from its location. So if we consider the height of these particular features on the leeward side, that distance would be 10 to 15 times of height of that particular barrier. Whereas, as we consider certain less dense barrier as shown here in this sketch, it will allow the more passage of the wind through that barrier. It will cause the reduction in the overall wind speed further downwind even as compared to this first example, as it is 25 times of height. These particular concepts we are using in view of the pollutant concentration likely to occur downwind. So this concentration will be high if the wind speed is low. Based on the same concept, IS formula suggests the expression to work out the plume height, which also tells that it is in the inverse proportion with the wind speed. As we try to understand the meteorological concepts, we must be in a position to understand the wind velocity as well as its intensity, its strength, its direction. And in order to measure these parameters, the instrument that we use are called as anemometers. Usually, this wind velocity is expressed in terms of meter per second. If we refer to certain specialized areas, it could be expressed in terms of nautical miles per hour as say knot. So it is equivalent to 0.51 meter per second. One more thing that we have to understand, though we are making use of this variety of anemometers, say this is cup and cone type, there is certain old conventional means, wind vanes, there are certain now digitized version, certain blowovers are there, even the balloon tide could be giving the direction, handheld are available, as well as even certain digitized versions are available. So in order to maintain the uniformity, this wind direction is always measured relative to true north, which is indicated by the axis joining the true north pole and true south of the earth, and is not reported to the magnetic north, that is the magnetic north pole, which is given by freely suspended magnetic needle. Also, typically the wind directions are mentioned with certain specialized terminology. Say for example, the easterly wind. So this easterly wind blows from the east, or say 90 degrees. Southerly wind from south or 180 degrees. Westerly winds from the west or 270 degrees, and accordingly. The conventional means to show the wind speed as well as the frequency distribution of wind direction, this wind rose diagram is drawn. As you see, for both of these cases, you can have that particular data expressed in relation with the quadrants northeast, east south, southwest, or west north. Or otherwise, it can be reported at 8 primary directions and 8 secondary directions as presented in this particular diagram. As we refer to this polar coordinate, the frequency of the wind is in proportion with that length. So you can see here, this thin line is indicating 0 to 2 meter per second, slightly broader 2 to 4 meter per second, and accordingly. So as you refer to certain line here, over this 0 to say around 8% of the times, the wind velocity is 2 meter per second. Whereas from this east northeast, for this proportionate time period, wind velocity is changing from 2 to 4 meters per second. This central region is telling us about the calm condition. So this calm condition is considered to be situation during which the wind is moving at less than 1 knot, that is 0.51 meter per second. This is very handy tool, and old versions as well as even the modern versions of these windrows diagrams can be adopted for the air pollution dispersion studies. As we discussed last time, atmosphere is associated with the air and it is always in motion. As we think of this motion, its scale as well as the magnitude varies considerably. As you see here, this is equator and this is the polar region. So as we think of these particular parallel rays that are striking the earth are spread more towards the polar regions as compared to the equators. So the rays being more normal or vertical, they hit the equatorial region more efficiently as compared to what could be the happening near this particular polar region. Hence, as we consider the global effect, it causes the general temperature difference between the equator and poles, and hence it is the basis to have the air movement from the poles towards the equator and from equator towards the poles. So, these vertical motions certainly occur in the atmosphere, and one has to consider for the study of the weather as well as the movement of the pollutants. However, as we consider the x direction on the previous slides, it is the major factor which would be helping us in order to determine the concentration that will be occurring in the downwind side. Hence, instead of considering the effect in the y direction or z direction, only the horizontal component of that particular velocity is considered. As we consider the regional scale, the winds can be easily understood by considering the balance of the various forces in the atmosphere. Giving consideration to the laws of motion, we have to take into account three basic sources in order to understand this horizontal motion, and the forces that are causing this motion are pressure gradient force, gravitational force, and the friction. We thought of this atmosphere, the gaseous envelope which is surrounding the Earth's surface. It is firmly attached with the Earth. And this attachment is only because of the gravitational force. So the gravitational force compresses this Earth's atmosphere to create the air pressure. This air pressure is causing certain densities to occur. As the densities are different, it induces the driving force for the wind. As we consider the lower spacing between the adjacent higher and lower pressure zone, it will cause more stronger wind to move from the high pressure zone to low pressure zone. So the difference in pressure from one location to other location causes the pressure gradient, and this pressure gradient is indicated by the proximity of the isobars. So that isobar can be defined as lines joining the stations having the constant pressure, very similar to our contours. So on the surface weather map, the tightly closed isobars will be showing large pressure gradients. If we consider the unit value, the atmospheric pressure can be determined as product of the density and the gravitational force, that is occurring in the vertical downward direction. So there is a temperature gradient, the way we discussed about the change in the geographic locations. With that, there will be horizontal temperature gradients. Because of non-uniform heating, there will be formation of the density gradients, and hence this pressure gradient force can be worked out as delta P divided by rho delta x, where this delta P is the horizontal pressure difference over the distance delta x. The direction of this pressure gradient force, as we are considering these isobars parallel to each other, is from high to low pressure belts. In addition, we have to take into account the effect of the Coriolis force. This Coriolis force is the resultant of the spinning motion of the Earth's surface. If any object is not firmly attached to the Earth, and if it is not influenced because of the gravitational force, it has to move in the straight line. However, as the object is attached or influenced with the rotation, this straight line motion will be changing its pattern, which will be noticed by someone who is rotating on the who is standing on the earth and is rotating with the earth. So that deflection with respect to that particular straight line motion towards the left or right as it appears is termed as Coriolis force. Certain equation is derived by Gaspard Gustave de Coriolis. So this Coriolis force is given by V 2 omega sine phi. So that omega is the angular speed of the Earth's rotation and the V is the velocity of the motion and phi is latitude. The Coriolis force, as we consider its action, it is on the right side of the wind vector in the northern hemisphere, whereas it is on the left in the southern hemisphere. Also, this Coriolis force is maximum at the poles, and as the object is moving along the equator freely, this force will be zero. Let's try to understand the magnitude of the Coriolis force and corresponding deflection. Here we are taking certain example. Let's consider wind velocity of the 10 meter per second blowing at say time 1 in the 0 degrees longitude meridian across the north. The wind in an absolute sense continues to blow in this direction for 1 hour, and the parcel of the air which is starting at the pole at time 1 will be traveling the distance of 36 kilometers because it is traveling with a velocity of 10 meter per second. So as viewed from the space, which is taken as the absolute frame of the reference, this flow is taking place is straight line. However, as we consider the rotation of the earth, we know that it rotates 360 degrees every 24 hours, that is 15 degrees per hour from west to east. Hence, in this specified duration of an hour, it has rotated 15 degrees. It has rotated 15 degrees. And hence, at time 2, that is 60 minutes after this time 1, the 15 degrees meridian is now beneath that wind vector. So as we thought of this Coriolis effect and its quantification by this equation, the angular speed can be determined as 7.27 into 10 raised to minus 5 per second as presented here. By making use of this expression, velocity is 10 meter per second, angular speed as worked out as 7.27 into 10 raised to 5. Sin phi being 90 degrees, it will be 1. Hence, this deflecting force can be quantified to be 1.45 into 10 raised to minus 3 meter per second square. Also, as we consider this portion of the circumference, it can be quantified as r into pi into pi by 180 degrees. Here this pi is the angle subtended by this sector at the center. So 36 degrees into that 36 kilometers into 15 degrees into pi by 180 degrees will help us to work out that deflection as 9.43 kilometers. Having discussed about now the Coriolis force as well as the pressure gradient force and the way they act, the effect of the rotation and the subsequent effect of the Coriolis force on the deflection, we can discuss about the geostrophic wind. Let's consider the high pressure zone and low pressure zone as represented here. So this PGF will be causing from high to low. As we consider these isobars, due to the effect of Coriolis force, this wind turns to rotate. It appears to turn to the right in the northern hemisphere and to the left in southern hemisphere. The ultimate result of this Coriolis turning is to balance the PGF and creates the wind that blows parallel to these isobars. So the wind caused because of the balancing of the pressure gradient force, Coriolis force, and hence the movement causing parallel to the isobars will be inducing geostrophic winds. In reality, the winds are rarely exactly geostrophic. However, as we consider the upper troposphere, the approximation would be reasonably acceptable. This is because winds are only considered truly geostrophic when isobars are straight and there are no other forces acting on it. As we extend the concept of this geostrophic wind, in reality, the isobars can be considered to be curvilinear. So as that wind is moving along the curved path, we have to take into account the effect of the centrifugal force, which is causing the deflection in the outward from the center of the curvature. So, as we consider the low pressure system, there is the appearance of this curvilinear isobars in form of these troughs. Here, the wind is blowing parallel to the isobars at lesser than geostrophic, that is subgeostrophic wind. As we consider the high pressure system which is giving the appearance of this ridge, the gradient wind blows parallel to the isobars faster than geostrophic, hence that are expressed as supergeostrophic winds. In the case of this curvature around low pressure, the balance of the forces occurs when the pressure gradient force equals the sum of Coriolis force and centrifugal force. However, in these high pressure systems, the balance of the forces would occur when sum of pressure gradient force and centrifugal force equals this Coriolis force. To maintain the given gradient wind speed, a greater pressure gradient force is required in the flow around the low pressure system as compared to high pressure systems. As we are trying to understand the occurrence of the wind and as it is influenced because of the various forces, the physical hindrance in form of friction, as we discussed on the initial slide, should also be taken into account. So, the surface of the earth, which is irregular, which is rough in manner, it exerts the frictional drag on the air blowing just above it. As we discussed on the initial slide, it will alter its direction as well as it will cause the reduction in its velocity. So these terrain conditions directly affect how much friction is exerted. Say for example, as we consider the ravenous conditions, broken hillocks, mountains, this will cause more slowdown or cause the change in direction as compared to the flat ground or say calm ocean surface. At higher altitudes, the surface features affect the wind less until we can treat that wind to be geostrophic. So the altitude up to such effect can be considered to be top of boundary layer. So as we discuss about the example of the forest or hillocks or calm ocean, the height of the boundary layer can vary depending on the nature of the terrain as well as various wind and temperature profiles. Also, the time of the day, obviously driven by solar insolation, as well as even the sun path driving the seasons, will affect the height of boundary layer. According to the literature, we can Assume this boundary layer existing about 1 to 2 kilometers above the surface. The effect of the friction is presented with this sketch. We consider that total pressure, gradient force and Coriolis force are getting balanced when the isobars are parallel to each other, which is causing the geostrophic wind to travel parallel to the isobars. However, as we consider now the effect of the friction, this is changing the direction of this geostrophic wind and having the flow from high pressure system to lower pressure system. This friction layer is slowing down the wind direction. Hence, whatever the geostrophic condition that we considered here, it in reality, because of the effect of the friction, it won't be geostrophic situation. So, this slowing down, as it is in proportion with the motion, it will cause the reduction in the Coriolis force, and hence here this pressure gradient force will be more dominant. As this pressure gradient force is becoming more gradient, this geostrophic wind direction, which was present in the absence of the friction, will be slightly deflected towards the lower pressure. The meteorologists call the difference between the total and geostrophic winds as geostrophic winds. So thanks for your attention. Here we made an attempt to understand the theoretical aspects of the wind circulation. In order to understand the effect of the pollutants on the global scale as well as local scale, we must understand the variety of the wind patterns that would be driven locally as well as globally. As we are attempting to understand certain micro pollution dispersion aspects, in the coming discussion, we will understand the local wind patterns and their impact on the dispersion of the pollutant. So bye till then, I wish you very happy learning. Thank you.